to the first symposium at Eastern Illinois University for Science and Technology. Dr. Stephen Daniels and myself wish from the depth of our heart that this would be the last. And maybe you will be the ones who continue this tradition. I want you really to take 2 copies of this when you go out. I'll put these on the side. One for you and a friend, and one for your grandkids. So after 50 years, you would come here in homecoming and you tell your grandkids, I was part of the first EIU symposium. Maybe there will be 50 of them over the years, but I hope that you feel the privilege of being part of history as we do these sessions. I'll not take much time to introduce our speaker because I think he needs no introduction. But I'll ask the chair, Dr. Stephen Daniels, who is really a wonderful partner in doing all this. So please give us some words. Thank you very much.
Well, I want to welcome you all here. Thank you for coming. I'm very excited to introduce Dr. Don Pakey. I've been a longtime colleague and good professor in the university and here in the physics department. We really appreciate what he has to say, and we'll hear about Albert Einstein's revolutions. So
that's
with that, it's yours.
Okay, well, I guess you've had time to read the Calvin and Hobbes, I hope. This gives us the essence of relativity right there, so I should just skip the rest of the talk. But anyway, what I'm really going to talk about is a little outline. I'm going to give just a brief discussion, sort of what's it all about. And then we'll spend a little bit of time on his miracle year, 1905, in which Einstein, at the age of 26, came out with 4 or 5, depending on who's counting, sort of groundbreaking articles that laid the groundwork for relativity, amongst other things. And then, this is really the heart of the talk there, we just talk about relativity and lots of the, what it really is and some of the really more cool and mind-blowing parts of it. And then I'll have very little to say about the last part, but we'll see how that goes. Okay, you know what, actually, let me ask you, before I even maybe memorize that for now, I'd like you to tell me what you think relativity is. Just throw out some concepts that you think are in relativity. You Physics 3 students can start because you better know. Anything. What's in relativity?
Black holes.
Black holes. The biggie. Black holes. Anything else? What else we have? Light. What about light?
Can't go faster than the fastest speed.
All right. The ultimate speed limit. Speed of light.
Speed limit, yeah.
Anything else?
Time perspective.
Yeah. Time depends on your state of motion. Time runs differently for different people. Anything else? Simultaneity, another idea about time. If one person says 2 things happened at the same time, somebody else might not agree. Okay, well, let's just, those are some of the big ideas of relativity. So first of all, there are 2 theories of relativity. The special one, which is a special case of the general one, and Einstein came up with this special theory of relativity, SR, in 1905, and these are some of the main ideas of it. Yeah, what somebody said, the speed of light is independent of the source and the observer. So I'm just going to kind of lay these things out real fast now and then go into them all in a lot more detail. So, maybe if you've never heard of this stuff at all, it'll sort of start working its way into your brain a little bit. And then by the second time you hear it, maybe it'll make a little bit more sense. Space is 4-dimensional. Now that's a fun thing to say, isn't it? Space-time. Time and space are together in one context. Then some other things that people said, time intervals depend on how fast the observer is moving. Lengths, there's length contraction. Things get shorter when they're moving very fast. C is the ultimate speed limit. It's the law, not just a good idea. Okay? So, and then philosophically, it sort of throws out the whole idea of an absolute state of motion. You cannot say that you are sitting still or moving. I kind of look like I'm standing still here, but the Earth is flying through space at a high rate of speed. Is there anything really different about that? The answer is no. Okay. a kind of unification of electricity and magnetism. And then, nobody said this, but probably the most famous equation in 20th century physics, E equals mc squared. I should have put it in a bigger font, Anyway, but what's special about the special theory of relativity is that it's restricted to observers that are moving with a constant velocity. Velocity, one of those physics terms, but I think we all know that. Well, the other half of it is the general theory of relativity, and that's the one with black holes, curved space, and all this kind of fun stuff like this. And I tossed an equation up there, but don't worry, you won't be required to solve that until the end of the hour. Right, Jim? Okay. Yeah, and the idea here being, I'm actually going to show, we don't have a pointer in this room, do we? Oh, that would be great, that would be great. Okay, yeah. What this equation means is that this thing right here is something that tells how space-time is curved. What this thing is something that tells you how much matter and energy are around. So in mathematical lingo, it says this, that matter and energy curve space-time. Oh, thanks. Okay, so that button right there? Okay. Ah, great. Okay. So curves space-time. So some consequences of this are that gravity bends light, and a good example of that is gravitational lenses. Now, this stuff can get, well, up to a certain point, people start wondering if it's really true or not. But this is a real, actual photograph. And what it's a real, actual photograph of is one quasar behind a galaxy. And because of the bending of light, we see 4 images of it. So the light is bent. There's a galaxy out here someplace, and there's a quasar, an extremely luminous object in the background. But we're seeing 4 images of it there. So there it is. It's true. It's real. You may not see that every day, but it's something that can be observed. Let's see. What else? We'll, of course, talk about black holes. Well, since matter and energy curve space-time, time is part of space-time. So, in fact, gravity does affect the rate of flow of time. Just say a couple words about gravitational waves. And then the big picture. The Big Bang. Not the TV show, the actual event. An expansion of the universe. Okay, so that's the brief overview of everything we're going to talk about. Okay, so according to our plan, we want to talk about Einstein in the year 1905. I have very little time to talk about his life because I ended up putting all this cool, physics stuff in there. But that's, I'm sure you'll agree, the most important part anyway, right? But anyway, the story is that in 1905, Albert Einstein was a patent examiner. A Swiss patent examiner, didn't really have a whole lot of connection to the community of physicists. And he was talking to people and he was able to read some physics papers, but he sort of, in 1905, published 4 papers, or 5, there's another one that's sort of in there too, but these are the 4 ones that are mentioned in the Annalen der Physik. And so we're just going to go through those in not too great of detail, but sort of amazing that this 26-year-old guy, that's what he looked like in 1905, was able to sort of come up with these groundbreaking ideas that really laid the groundwork for a whole lot of 20th and 21st century physics. Right. So, okay, there he was. Living with his wife and child in a small apartment. Right, I just said all that. Okay, fine. Okay, so the first one, what happened to my title? Oh, guess I should have. Yeah, okay. Anyway, oh, right, okay, I'm sorry. Right, so this first paper actually has nothing to do with relativity. Of the 4 papers, 2 of them had to do with relativity, but 2 didn't. This was actually the photoelectric effect, which all of you Physics 3 students are complete experts on. And that's actually what he got his Nobel Prize for in 1921. Also, it turns out that when his marriage with his wife was breaking up, they made this agreement. He said that he would win the Nobel Prize, and when he did, he would give her the prize money. And she thought about it for a while and said, okay, sounds like a good deal to me. Actually, I don't know whether he actually did. I'm assuming he did. He was a man of his word as far as I know. So anyway, that was the photoelectric effect, which was, again, a very groundbreaking paper. He proposed the idea of photons, particles of light. In fact, that's the way we think about light these days. We think, light coming from the ceiling, light right here. It looks kind of continuous, but there's good evidence. We all believe it these days that it's actually an extremely large number, trillions and trillions per second of individual particles of light called photons. So, okay, the second one, on the motion of small particles suspended in a stationary liquid is required by the molecular. The names of these things, they didn't really tell you a whole lot what they are, right? But this one was about Brownian motion. Some of you might have learned somewhere about Brownian motion if you look, there's different versions of it, but if you look through a telescope at maybe water that has any little particles, like pollen grains is what they used to use, you can see them bouncing around, right? That's the Brownian motion. And he interpreted this as that they're being hit by individual atoms. And the atoms are too small to see. I mean, they didn't have, well, at that time they were completely too small to see, but you could actually see their effects. And actually, this is something that I found out in doing the research for this talk, that at that point, the atomic theory was still controversial. A lot of scientists thought of atoms as being kind of a useful computational tool, but not necessarily real. I had not realized that late in the game that there was any question as to whether atoms actually exist or not. So this is another extremely groundbreaking article. There were famous scientists who were quoted as saying that basically they didn't believe in atoms until that point. And then with his clear explanation of the effect of atoms, it proved to them that atoms actually exist. So, by the way, anybody can ask questions whenever they want to, or tell jokes, as long as they have to do with relativity. Okay, good. And 2 papers on relativity. Okay, I want to give the credit to Dave Linton, who actually went there to Einstein's apartment in Bern, Switzerland, and took a bunch of pictures. And what he said was important about this picture, and it doesn't really show it because you can't take a picture of a whole room, but he says that you see, where is it? Okay, hold on, I think I've got it on the same page here. Where is it? I didn't put it on there. Okay, there's a famous picture of Einstein standing at that very lectern, writing. And what Dave says, Dave Linton, who will be giving a couple of talks in this series, he's giving one on the Copernican Revolution and one on his own odyssey of astronomy. Anyway, what he said was that by being there, it's a museum now, right? It was clear that the apartment was so small that he had to stand up to do his papers. So that's why I included that. Also to thank Dave for giving me some photos to look at. Okay, so this is the third of his 4 famous papers in this year on the electrodynamics of moving bodies. And again, you can't really decode that without knowing more about it. But this is the one in which he outlined his special theory of relativity. So you know what, we're going to do more with it later, so we're just going to kind of go on. But it postulates, this is a big thing in relativity. A postulate is an assumption. You just assume that something is true, and then you see what are the consequences of that. If that's true, like that time doesn't run at the same rate for everyone, what does that really mean? That's not one of the postulates, but we'll see it's one of the consequences. So there's that. And then the 4th paper you might guess is general relativity, but you would be wrong. Okay, oops, I didn't get there yet. Okay, but one of the other consequences, like I already said, is that all motion is relative. Okay. And time is different for different people. Okay, right. And then finally, the 4th paper is actually more of special relativity. This is where we get to the final one. I put it on here twice now, E = mc squared, so let's keep track. So does the inertia of a body depend on its energy content? So that was just sort of more of special relativity. Well, here we go. So that was the fast version. Let's look into it in a bit more detail and see, what it's really all about. So, proofs, consequences, paradoxes. And, I hope that somewhere in there, if you've never really read or heard much about relativity, you'll at least come to believe that it's true and have some kind of understanding of it. It is understandable, actually. Some parts are very weird. Okay, well, let's start out here. So, one of the postulates that he came up with was the fact that the speed of light is the same for all observers. Now, so what does that really mean? Well, let me just kind of briefly explain that, right? So let's say you're driving down the road at 60 miles an hour in your car. All these Physics 3 students are saying, I heard that one, Anyway, driving down the road in your car, 60 miles an hour, and you throw a baseball, forwards at 20 miles per hour, right? So if somebody is standing by the side of the road, they're going to see it coming at them at 60 plus 20. That's the math part of the talk. That's 80 miles per hour, right? Right. Well, it turns out that that's not exactly true. We'll find out. We won't find out later, but we would if I was doing that. That the true answer is more like 79.9999999 something. Okay, but then you have to ask the question: what about the headlights of the car? Car's going along 60 miles an hour. You turn on the headlights. So somebody's standing up by the side of the road with their light speed detecting apparatus. What speed will they see? Do you add the 60 miles per hour onto it or not? The answer is not. In fact, the speed of light is the same for all observers. And this seems, either impossible or just wrong or something. But we're going to see how it can actually work out. Right. And then well, let's just do it. Okay. So this may look even more familiar. Okay. So I'm going to lead you guys through this one. Einstein did a lot of what he called, because he spoke German, Gedanken experiment. It's a thought experiment, right? He wasn't much of an experimentalist, and besides that, he didn't have access to any laboratory equipment, right? He was just, off in his apartment there. So he thought about things. And so this is a thought experiment. And this is an example of using the postulates, the things that you're assuming, to find out what the consequences of that are. So here's the idea is, okay, it seems like experiments show, and also just thinking about it, seems to indicate that the speed of light is going to be the same for observers. So what does that actually mean? Well, what we'll do is we'll make this, we'll have a little device, and you can't really see it in the picture, but we'll call it a light clock. This is not a real device that really exists, but it could. So what it is just something that emits a little pulse of light. And it goes up, it hits a mirror, and it comes back down, right? So light, travels at a finite but fast speed, 300,000 kilometers per second, or 186,000 miles per second. That's pretty fast, but still it takes a little bit of time, to go up and down. And so what you want to do, and we do this in relativity all the time, is look at it from different people's point of view. Okay, so from her point of view in this train, it goes up and down, D up and D down, and takes a certain amount of time. But then, what about somebody standing by the side of the track? And this is a thought experiment that Einstein actually thought of. Let's say the train is moving along. Now, for this to be a significant effect, the train would have to be going really, really fast. But nevertheless, it illustrates the principle. So what does this person see? This person sees the light going up and down, but at the same time it's going up and down, it's also traveling this way. So, so this person sees the light going on this longer path. Now here's the part where we have to really kind of concentrate a little bit and see what this means. According to the postulate of special relativity, both these people should see the same speed of light. But this person sees it going a longer distance with the same speed, therefore a longer time. And that's the essence of the argument, that time has to run at different rates for different people. Now, if you're not convinced, we'll get to some experimental proofs in a few minutes. But you should be convinced. The logic is inescapable. Okay? Any questions? Okay. So again, no matter how you're moving, how the source is moving, you see the same speed of light. You will see the light coming at you at 3 times 10 to the 8th meters per second, no matter what. This person sees a longer distance, therefore a longer time. And if this person was sort of looking into the, watching this person as they go by, this actually has nothing to do with light. It's time itself which is slowing down. So as this person goes by, if you could watch their watch, you would see it ticking slowly. It's time itself that's slowed down. Light goes up. Okay, so I'm sure I talked about everything I'm just going to put there. So that was it. Okay. Well, you could go, the math is pretty easy. The light goes up and down. There's a right triangle there. Pythagorean theorem, you get square roots and squares and stuff. But this is what you find. How much does time get slowed down when you go a certain speed? This is the answer. Now, the x-axis here is velocity as a fraction of the speed of light, and it doesn't go past 1 because that would be illegal, right? Okay. And this shows by what factor it slows down. So, when you get up close to the speed of light, it's slowed down by a factor of 8 or 9 or 10. It actually goes, infinitely if you got infinitesimally close to the speed of light. But most normal speeds, like most real trains, for instance, would be so far down here that this number would be indistinguishable from 1. The rate of change does not change significantly unless you're going pretty darn fast. Right. But is that true? Okay, so good. This is where we convince you that it's really true. This is an experiment from 1971, and there have been a lot since then, but these are the groundbreaking ones that first prove all these things. In this case, they took, they had 3 pairs of atomic clocks. Atomic clocks, that sounds pretty impressive right there, doesn't it? It's just a very accurate clock. Now, no clock is infinitely accurate, but we know what the accuracy actually is. And they flew them around on commercial airlines. This is the commercial airline stewardess right there, in different directions. And when they got back together, there were some very small time discrepancies, but they were consistent with relativity. And in fact, they had left some of the clocks stationary at the, Naval Observatory. And so it all worked out. It's a very small effect, but they checked it out in the fastest way that they could at that particular time. Okay, so it worked. Now here's another good one. The Frisch-Smith Muon experiment, 1963. So here we go. Muons are particles with a natural lifetime of 2.2 microseconds, 2.2 millionths of a second. And let's see, how am I? Right. And they're exotic particles. We don't really run into them all the time. We think about protons, neutrons, and electrons. But they're produced at the top of the atmosphere by collisions of cosmic rays, just high-energy particles coming from outer space, with atoms in the upper atmosphere. And so this is actually a pretty good direct proof also. So if there were no such thing as time dilation, they would decay before they reach the Earth. I mean, even if they're going the speed of light, and they are going really close to the speed of light, they would decay before they reach the surface of the Earth. And in fact, some of them were moving sort of 99.5% of the speed of light, time dilation factor of 9. And what is this graph? Well, maybe we should just say this is a graph that shows what it's supposed to show, I suppose. I can't even read that, but this is the data point. And this is the line that says with time dilation, and this is without time dilation, and this is how many muons do you actually detect. So if there were no time dilation factor, sorry, you can't actually read that. I should have made it a little bit bigger. But so anyway, in any case, it was a good proof. And this is for much faster, right? The airplane going around the Earth is a very small fraction of the speed of light, but this is a much more significant fraction. So like I said, the time dilation factor is like 9. Okay. Now we still can't do this with like human beings, right? That'd be the ultimate proof, I suppose. But I think this is, it's pretty good anyway. Right. Now if technology impresses you, it turns out the global positioning system, it's all programmed with, well, it has to be the equations of general and special relativity because the timing is extremely important. That's how GPS works, So it wouldn't be correct if the equations of relativity weren't correct. So they are. Okay. However, there are other theories about how one might test the special theory of relativity. This is kind of long. Well, okay, anyway, they're going to test it. They jump in the wagon, faster and faster, going pretty fast. What time is it now? 10:25. Time still hasn't stopped. Has it stopped now? No, just my heart. Then they crash. Well, it looks like Einstein's a fraud, wouldn't you say? No, he's right. Look, my watch isn't going at all anymore. So time is infinitely slowed down. So good old Calvin and Hobbes. Right, now here's an important point. No observer can ever observe their own clock. You'll never look at your watch and say, "Whoa, isn't that weird? My clock is going really slowly." You know, it's time. It's your own biological time. It's everything. It is time itself. It's not any particular physical processes. It's everything that slows down. So, you know, you can never notice your own time slowing down. However, there are real effects, which, you know, we haven't been able to do this one yet. But this is a famous, again, sort of thought experiment that people do in relativity. The twin paradox. There's two twins. At this point, they kind of look alike. And one of them blasts off on a fast space trip to another part of the universe and, you know, comes back. And when he comes back, the one who stayed on Earth is really old and this one is really young. And the elapsed, this person will feel as though they've aged as though a much shorter time has gone by from their perspective. And it's, you know, it's true. Like I said, we haven't actually been able to do this experiment, but we've done all the other versions of it. So that's the famous twin trip. Right. Now there's an interesting thing here. Somewhere along the line, I said there's no such thing as an absolute state of rest or motion. So like, what's special about the person who goes off in the spaceship as opposed to the person who stays on Earth? I mean, you already said that if I'm standing here, I'm not really standing here. The Earth is, you know, flying through space at a high rate of speed. So, you know, why does one person actually end up younger than the other? And the answer is that this is not really a symmetrical situation. Is that you know, the fact that that the one who travels had to go out at a certain velocity and come back, they had to turn around, slow down, and come back, makes an asymmetrical situation. So you can actually figure this out using just special relativity, but you know, it does work out. Well, but we can be a little bit more speculative about it then and say, well, what if that person were to go all the way to the center of the galaxy? How far is that? Well, you might know, it's 26,000 light years. Okay, this is the map of our neighborhood here. Where are we? I guess, well, there's the galactic center. So there's something, you know, going on in our galaxy. Good chance it's going on down there. We might want to go visit. So could we do that? It's 26,000 light years away. By the way, many people have a misconception about the word light year. A light year is not a long time, it's a long distance, right? It's a distance, it's not a time at all, right? In fact, it's the distance that light travels in 1 year, okay, a year, at 186,000 miles a second, which is pretty fast and pretty long. So it's so 1 light year is about 6 trillion miles, okay? So that's a long way. And so it's 26,000 light years to the center of the galaxy. You know, could you actually go? Well, without time dilation, if we have this law that says we can't go faster than the speed of light, then obviously it would take you at least 26,000 years to go there. So people don't live for 26,000 years, so you couldn't do it. But, you know, with time dilation, the trip could hypothetically be made in a human lifetime. Because, you know, if you go close enough to the speed of light, then because of the time dilation factor, your elapsed time. Now there's other kinds of arguments that you could make that say that we'll never be able to do this in a human lifetime, just because of the energy requirements and you know, and other things. But that's that. Okay, another consequence is length contraction. This is a fun one here. So not only does time, the phrases are time dilation and length contraction because times get longer, right? Time gets spread out. The time between one tick of the clock and the next tick of the clock gets longer. Well, lengths get contracted, it turns out. So the way that there's different versions of this, but this version is called the ladder paradox. So what you got is a 10-foot garage. Okay, it's 10 feet wide with automatic doors at the front and the back. Right. Sorry. Okay. And you have a 12-foot ladder. Okay. So what happens is when the front of the ladder gets to this, there are automatic doors, the door opens, and as soon as so then, it reaches the back of the garage, that door automatically opens, it's got an electric eye or something, and then you keep on going, right? So when the back of the door gets through that door shuts, and then if you go all the way through, then that door is shut. And the question is the ladder ever inside the garage with both doors closed? Most people would think that the answer is obviously no, because it's a 12-foot ladder and a 10-foot garage. So it can never be completely inside with both doors closed. But, yeah, you guessed it. Yes or no, depending on your frame of reference. Okay, so let's quickly look at both of these. So what we're doing here is we're saying, from the point of view of the garage, okay, you're standing by the side of the garage, the ladder comes flying by at a high rate of speed. It turns out that if you're going 60% of the speed of light, then the length contraction factor is 4/5 or 5/4, depending on which way you're going. So what that means is that in that frame of reference, the ladder is shorter, and it's actually short enough so that at one point it'll be completely inside there with both of the doors closed. Okay? However, if you look at it from the point of view of the person who's carrying the ladder, right? What do you see? You see a garage coming towards you at 60% of the speed of light, which means it is suffering a length contraction. So, which means that the garage is shorter than it was. So now it's 0.8 times 10, or 8 feet long. So the garage is shorter than the ladder. Therefore, it's never inside with both doors closed because the ladder's longer than the garage. But this also has to do with this idea of simultaneity. Because the whole question is the ladder ever in the garage with both doors closed? That means at the same time, right? Is there ever a time when this door is closed and this door is closed and the ladder's inside? And so it all comes back again to this idea of time, that that time is different for different people. Okay, so finally, we'll get to the most famous equation of the 20th century. Now, I think this is probably not an accurate depiction of the way that Einstein came up with this, but it sure is funny. There's several historical inaccuracies. First of all, he didn't just go through the alphabet and say ma squared, no. mb squared, nah. And the other thing was, he did it when he was much younger, as we found out. He did it when he was 26 years old. And third of all, he did not even have a big blackboard in those days. He had the tiny little apartment that we talked about earlier. So, but anyway, it's good fun. Okay, so, what does it mean? What's it about? Well, what it means, really fundamentally, is that mass and energy are two forms of the same thing. Sometimes we use a word like mass energy. You put a dash or a slash or something in there. So it's two different forms of the same thing. Kind of like space-time. We combine them together into one concept, space and time, mass and energy. Okay? And a good way to think about it is just to think of mass as a very highly concentrated form of energy. Particles are sort of like little things that are at a certain place, and energy seems to be sort of spread out in a way. But let's bring it down to the brass tacks here and see what it actually means. So let's say you got a wind-up toy like this one. You wind up the spring. So you're storing energy in it. The spring contains energy if you've wound it up, potential energy for the aficionados out there. Okay, so that means that its mass very slightly increases. According to this equation, equals, well, it is in fact equals mc squared. Okay. But it's very small because c squared is a darn big number. Speed of light in normal metric units is 300 million meters per second. That's 3 times 10 to the 8th meters per second. If you square that, you get 9 times 10 to the 16th, which everyone knows is a really big number. Okay, so what does that mean? It means just to have a normal amount of energy, the amount of mass change is going to be really, really small. So we come up with this idea of mass defect. We had to show the atom bomb because we always have to do that when talking about equals mc squared. But the idea is, in this case, what we did is we wound up a spring. But you can think of lots of other kind of examples, like a chemical process like burning. You take carbon and 2 oxygen atoms and put them together and make carbon dioxide. Okay, so you start out with a carbon here and oxygen there and an oxygen there. They all weigh something. They all have a certain mass. And then they're attracted to each other with certain electrical forces. And so they combine, that's what the burning process is, to make carbon dioxide. Well, that's actually a lower energy situation. Just like when I drop something, it's going to a lower energy, with gravity. And so what we'd find out is that the mass of the carbon dioxide molecule is very slightly less than the mass of the carbon and the oxygen that we put into it. And, this number, that number could be 8 or 10 or 7 maybe, but, it's a very, very small amount for typical chemical reactions. And so the reason that we always show atom bombs when we're talking about equals mc squared rather than, I don't know, firecrackers or something, is just because of the fact that the number is bigger for nuclear weapons or nuclear reactions. For nuclear reactions, you could actually, okay, so what this means is if the number is 10 to the minus 9, then that means that in a typical chemical reaction, you might lose one part in a billion. The mass goes down by 1 part in a billion. And so for a nuclear reaction, it might be 1 part in 10,000, which might still sound small, but you see it's like, 100,000 times more than in that case. And in fact, in the nuclear weapons that, the first ones that were actually used, the Hiroshima and Nagasaki bombs, you have a chunk of uranium or plutonium that's like 8 or 10 kilograms in size, and the vast majority of it's still there. You only lose that very small fraction. But, to destroy a city, you only need that much, right? So it's a difference in amount, but not in concept. Energy and mass are always related in that way. And I'm hoping I got another line in here. Yeah, okay. Right. So first of all, this one. In accelerators, particles are often created from energy. Yes, that happens all the time. And this is supposed to be showing, in this case, a gamma ray, a high energy photon of light comes in and hits something. It produces an electron and an anti-electron, and the other electron goes off in that direction. So this happens all the time. And that's how they create the very, they produce these very exotic particles just by, turning energy into matter. So, and what's this about? Well, I had to throw that in there. Well, I have to decipher this one for you. P stands for proton. And protons and neutrons are actually made of smaller particles called? Anybody? What are protons made out of? What is or elementary? But there are elementary particles, but quarks. That's it, quarks, right? And so, I looked up, so a proton is actually composed of 2 what we call up quarks and 1 down quarks. Those are just names that we give to quarks for fun, But it turns out that if you find the bare mass of a quark, the bare mass, that the mass of what makes up a proton is only less than 2% of the mass of what you get out of it. So I guess you'd say that the proton mainly just is energy, and then there's a way of thinking about things that really, waves and energy is really all that exists. Maybe Brittany Rutherford will tell us more about that in a few days. We saw this before, but it must be more fun stuff having to do with this. Okay, right. E equals mc squared is for an object which is sitting still at rest. For a moving object, the total energy is, I had to put this in here, gamma mc squared, where gamma is that same factor. That's what this number on here is, the gamma thing. So when the only reason I put that on there, I don't want to be too equation heavy, is to show that if you were to go, this is another argument as to why things cannot go the speed of light. If you were to go the speed of light, then this gamma factor, this time dilation factor, which is the same as the length contraction factor, which is also the factor by which the energy of a particle increases, would be infinite. So therefore, it would take an infinite amount of energy to accelerate an object all the way to the speed of light. So, it's not just hard to do, you just really can't do it. Okay. Right. Maybe many people have sort of heard that the mass of a particle increases with speed, and there's different ways of looking at it. But most people in modern usage just say the mass. When you say the word mass, you mean the rest mass. Do you agree with that, Jim? That's the common usage, is that mass means rest mass?
If you're an elementary particle guy, that's true. If you work in general relativity, it's the gamma mc squared because effectively it's nothing. So depending upon the field.
And there you have it. Okay. So I shouldn't say modern, I should say particle versus, okay, fine. Okay, well anyway, so that's all we're going to say for now about special relativity. Let's go on to general relativity. Okay, so what was special about special relativity, we said, was that it really only applies for objects going at with a constant velocity. So, and you may remember that the year in which he came up with his 4 famous papers was 1905. It took him 11 more years. He wrote a series of articles, but before he could generalize that to include the effects of acceleration. So here it is. General relativity is based on what we call the principle of equivalence, that the effects of acceleration are indistinguishable from those of gravity. Now, there's a nice little thought experiment. These are all Gedanken thought experiments. But just think of this first off. I mean, you know that if you get in an elevator, Einstein actually used elevators to talk about these things. When you press the up button and you start upwards, you sort of feel heavier, right? We learn how to analyze that in Physics 1, if you're in Physics 1 and all that sort of thing. But it kind of feels as though gravity suddenly got stronger, right? So this is Einstein's way of thinking, is he says, well, they kind of feel the same. Maybe they are the same. And so this is, in fact, the postulate. He says, what if they are really, really the same? What does that really mean? So this is the postulate. The effects, the equivalence, the effects of acceleration are indistinguishable from those of gravity. So if you want an experiment you can do is drop something, it falls down. Trust me, I've tried it. And so there's two interpretations of that. If you're inside of a closed elevator with no windows, it's because gravity is pulling it down. On the other hand, you might instead be off in the middle of space accelerating that way at a rate of 32 feet per second, 9.8 meters per second, and you would experience the same thing. Because in that case, the ball would basically just be hanging there in midair, but you and your spaceship are accelerating that way, so it looks exactly the same. And you would feel weight under your feet because your spaceship is accelerating like that. Well, Einstein said they don't just feel the same, they really are the same. And I'm going to go real fast on a lot of stuff because I see I'm talking too slow and I got too much stuff to talk about. But so I'm going to completely ignore that. Gravitational light bending, though. Okay, here's the deal. This is the way you do one of these Gedanken experiments for general relativity. You say, okay, I'm going to go inside my elevator, which has the ability of accelerating at a very high rate of speed. You can't really tell what's going on here, but in this particular case, what's happening is that the elevator is accelerating upwards, and you're shining a light across the elevator. Well, as the light goes straight across, you are accelerating upwards, so it appears that the light is bending downwards. Well, Einstein says that has to be equivalent to the other situation where I'm not accelerating at all, I'm just sitting on the surface of the Earth. And so the light, therefore, according to this logic, gravity has to bend light. And in fact, it's true. Now, when I shine a beam of light across this room, you may not notice it. But here's the deal. If I throw something, and I won't, across the room, it curves over in a certain path because it's accelerating downwards at a rate of 9.8 meters per second. Light does exactly the same thing, but it doesn't take very long to get from here to there at all. So it doesn't fall very far. It goes downwards at the rate of 9.8 meters per second. Okay? Well, that's not really noticeable if you're talking about Earth gravity. Sun weighs more. Maybe it's got more gravity. In fact, this is the first really decisive proof of general relativity. So here's the deal. Gravitational light bending due to the sun. Okay, so light goes by the sun. It gets bent. Us on Earth see it appear to come from there. Two problems with this. One, the actual angle is 1.5 arc seconds. A second is a 60th of an arc minute. A minute is a 60th of a degree. So it's really, really small. The other thing is you can't really see stars in the daytime because the sun's out and the sun's really bright. So you have to do it during an eclipse. They did, and they proved it. It actually worked. Gravitational lensing that I already talked about is an example of this. Okay. Let's see. Right. And we've all seen this analogy here about how it is that gravity bends space-time. Another consequence is what's called gravitational waves. So, you know, what this is supposed to be is maybe two stars, two black holes, two neutron stars, or something going around each other, and they actually produce waves in the gravitational force. And so, if a gravitational wave goes by you, it makes you experience a force that kind of does this, although it's extremely, extremely small effect. Well, people are attempting to detect them directly. So far, no luck, but you know, we're hopeful that in the near future we will be able to. But they have been detected indirectly by the, in a situation like this. These stars that are going around each other are constantly losing energy because they're giving off gravitational radiation. And I see I've vastly overestimated the amount of time that I have. So let's see. I think, yeah, it's doing okay. Okay, right. So black holes, right? We've got to talk about black holes. There's an artist depiction of a black hole. Okay, so here's the deal on this. Now we talked about how, you know, gravity bends light. Well, in fact, if you put enough mass in a small enough area, volume actually, then nothing, not even light, can escape. That's why we call it a black hole. They've been observed, both stellar mass and supermassive. Okay, two things here. First of all, what do we mean by observed? If not even light can escape? Well, the answer is there's really strong gravity around these things, and so they cause a lot of very extreme situations. Matter will be streaming into them and sort of heating up and giving off X-rays and other high-energy particles before it falls into the black hole, so we can observe them. It's, you know, funny, when I was a graduate student back in the 1980s, and I was in astrophysics, we always called them black hole candidates. And then sometime during my graduate school career, Cygnus X1 in particular started to be called a black hole, not a black hole candidate. In other words, the observations and the theory got good enough that everyone was convinced that they really are. And in fact, now we believe that there are supermassive black holes at the centers of almost all galaxies. Our very own galaxy that you might think of as a fairly safe place has one with a mass of 4.1 million suns at the center of our galaxy. Gives off a lot of energy. Black holes, what are they? Yeah, well, you know, you could say that a black hole has two parts. There's this so-called event horizon. There's nothing actually there, but that is the point beyond which nothing, not even light, can escape. And then there's what we call the singularity at the center, which is, you know, singularity, if you've been in a math course, means something is infinite. So in this case, we'd say the density is infinite. A star or something has collapsed down to sort of a mathematical point. We can't really completely honestly say it goes all the way to a mathematical point because our theory breaks down at that point, but we know it gets darn small. So that's it. And so if you were to fall into one, what would it look like? Well, you get stretched out by the tidal forces because your feet are closer to the black hole than your head, and that would be an unhappy situation. But an interesting thing about this is that there is is it on this slide? Well, next slide, or maybe I'll say it now. It must be here. Ah, there it is, yeah. That there's gravitational time dilation. That the gravitational time dilation factor is actually infinite right at the what we call event horizon of it, which means what? That even though the person who went into the black hole would be dead, from somebody's point of view watching them go to the black hole, they never appear to get there. They just get closer and closer and then sort of asymptotically approach the black hole and never actually get there because of the gravitational time dilation factor. Time is so stretched out that they never appear to get there. And if you keep watching them, you just wouldn't be able to see them after a while because there would be only a certain amount of photons of light that are leaving the person that you could observe. So it becomes longer and longer in between photons of light being emitted, and so they just sort of fade out and you cannot see them. So, Big Bang cosmology and the expanding universe. Oh, God. Okay. I got to think of a good place to stop here. Oh, yeah, okay. We'll get through this. We'll do this. Okay. Right. So yes, in fact, Einstein's theory of general relativity theory gives us the overall shape, shape and time evolution of the universe itself. And so, this is a depiction of the Big Bang. We all know that the universe is expanding. And I'm not going to say much about it. We now have it pinned down pretty well that the Big Bang occurred about 13.8 billion years ago. Okay, so here's a strange one. I'll just do like 2 more slides after this, so we can leave and stuff. But okay, so general relativity is a theory of gravity, which kind of supersedes Newton's theory of gravity. I mean, Newton is fine in its realm, but this is a more broad, more precise theory of gravity. And one thing it says is that the gravitational force, we don't really think about things in terms of force and general relativity, but if we did, we would say that there's a velocity-dependent aspect of it. So, for instance, if you were like hanging, let's say, you're like outside the Earth's rotating. A rotating mass would actually cause you to rotate a bit like that. It's that kind of force, not just an attractive force, but a force that drags your frame of reference around. So this is a really great thought experiment now. So, if I do this, my arms like go out from my sides. You may have done that. Why is that? Well, because you're accelerating, you look at it in terms of like centrifugal force or something like that. But there's a problem here because, my hands don't go out when I'm standing here and they do when I'm rotating, but rotating with respect to what? Didn't we just say that all motion is relative? Well, in fact, it should be the same. So if I'm doing this, it's exactly the same as if, in fact, indistinguishable from me standing still in the entire universe going around that way. And they really are indistinguishable. Does anybody have any questions? Actually, I got 2 more slides, but I'm going to finish them up because I know we got to go. Okay. You know what? I'm going to completely ignore that. Yes, Einstein was really smart. His work did rest on that of other people. But the main thing, really, is that he was a person who had the ability to question the most basic assumptions. And this came into everything he talks about, culturally and in physics and everything. He didn't really accept anything as the truth. He examined it. So, and let's see, I'm sure there's something else important that I wanted to have on here. Yeah, it gets even wilder than that in terms of ideas that physicists have these days. One universe isn't enough. We have all these different universes. We talk about if you go far enough away in space, there might be sort of another entire universe. We have the quantum mechanical multiverse where we have these different parallel universes and all that sort of thing. And so people are thinking about these things. And we don't have time to talk about it at all, so I won't. But I kind of feel as though physics has really kind of exploded in the last century, especially. There was a time when we kind of thought we understood what was going on, but now we find out that the more we know, the less we know. So I will finish by saying that the quest for knowledge continues, and to thank our symposium organizers. What we conceive.
Welcome to the first symposium at Eastern Illinois University for Science and Technology. Dr. Stephen Daniels and myself wish from the depth of our heart that this will be the last. And maybe you will be the ones who continue this tradition. I want you really to take 2 copies of this when you go out. I'll put these on the side. One for you and a friend, and one for your grandkids. So after 50 years, you would come here in homecoming and you tell your grandkids, I was part of the first EIU symposium. Maybe there will be 50 of them over the years, but I hope that you feel the privilege of being part of history as we do these sessions. I'll not take much time to introduce our speaker because I think he needs no introduction. But I ask the chair, Dr. Stephen Daniels, who is really a wonderful partner in doing all this. So please give us some words.
Some words.
Thank you very much.
Well, I want to welcome you all here, and thank you for coming. I am very excited to introduce Dr. Don Pakey. I've been a longtime colleague and good professor in the university and here in the physics department. We really appreciate what he has to say, and we'll hear about Albert Einstein's revolutions. So
That's
with
it.
that, it's yours.
Okay, well, I guess you've had time to read the Calvin and Hobbes, I hope. This gives us the essence of relativity right there, so I should just skip the rest of the talk. Or five, there's another one that's sort of in there too, but these are the 4 ones that are mentioned in the Annalander Physik. And so we're just going to go through those in not too great of detail, but sort of amazing that this 26-year-old guy, that's what he looked like in 1905, was able to sort of come up with these groundbreaking ideas that really laid the groundwork for a whole lot of 20th and 21st century physics. Right. So, okay, there it was. Living with his wife and child in a small apartment. Right, I just said all that. Okay, fine. Okay, so the first one, what happened to my title? Oh, guess I should have. Yeah, okay. Anyway, oh, right, okay, I'm sorry. Right, so this first paper actually has nothing to do with relativity. Of the 4 papers, 2 of them had to do with relativity, but 2 didn't. This was actually the photoelectric effect, which all of you Physics 3 students are complete experts on. And that's actually what he got his Nobel Prize for in 1921. Also, it turns out that when his marriage with his wife was breaking up, they made this agreement. He said that he would win the Nobel Prize, and when he did, he would give her the prize money. And she thought about it for a while and said, okay, sounds like a good deal to me. Actually, I don't know whether he actually did. I'm assuming he did. He was a man of his word as far as I know. So anyway, that was the photoelectric effect, which was, again, a very groundbreaking paper. He proposed the idea of photons, particles of light. In fact, that's the way we think about light these days. We think, light coming from the ceiling, light right here. It looks kind of continuous, but there's good evidence. We all believe it these days that it's actually an extremely large number, trillions and trillions per second of individual particles of light. How much matter and energy are around. So in mathematical lingo, it says this, that matter and energy curve space-time. Oh, thanks. Okay, so what's that button right there? Okay. Ah, great. Okay. So curves space-time. So some consequences of this are that gravity bends light, and a good example of that is gravitational lenses. Now, this stuff can get, up to a certain point, people start wondering if it's really true or not. But this is a real, actual photograph. And what it's a real, actual photograph of is one quasar behind a galaxy. And because of the bending of light, we see 4 images of it. So the light is bent. There's a galaxy out here someplace, and there's a quasar, an extremely luminous object in the background. But we're seeing 4 images of it there. So there it is. It's true. It's real. You may not see that every day, but it's something that can be observed. Let's see. What else? We'll, of course, talk about black holes. Well, since matter and energy curve space-time, time is part of space-time. So, in fact, gravity does affect the rate of flow of time. Just say a couple words about gravitational waves. And then the big picture, the Big Bang, not the TV show, the actual event, an expansion of the universe. Okay, so that's the brief overview of everything we're going to talk about. Okay, so according to our plan, we want to talk about Einstein in the year 1905. You know, I have very little time to talk about his life because I ended up putting all this cool, well, okay, physics stuff in there. But that's, I'm sure you'll agree, the most important part anyway, right? But anyway, the story is that in 1905, Albert Einstein was a patent examiner, a Swiss patent examiner, didn't really have a whole lot of connection to the community of physicists. And you know, he was talking to people and he was able to read some physics papers, but he sort of, in 1905, published 4 papers. But anyway, what I'm really going to talk about is a little outline. I'm going to give just a brief discussion, sort of what's it all about. And then we'll spend a little bit of time on his miracle year, 1905, in which Einstein, at the age of 26, came out with 4 or 5, depending on who's counting, sort of groundbreaking articles that laid the groundwork for relativity, amongst other things. And then, this is really the heart of the talk there, we just talk about relativity and lots of the, what it really is and some of the really more cool and mind-blowing parts of it. And then I'll have very little to say about the last part, but we'll see how that goes. Okay, you know what, actually, let me ask you, before I even maybe memorize that for now, I'd like you to tell me what you think relativity is. Just throw out some concepts that you think are in relativity. You Physics 3 students can start, because you better know. Anything. What's in relativity?
Black holes.
Black holes. The biggie. Black holes. Anything else? What else we have? Light. What about light?
Can't go faster than the fastest speed.
Right. The ultimate speed limit. Speed of light.
Speed limit, yeah.
Anything else?
Time perspective.
Yeah. Time depends on your state of motion. Time runs differently for different people. Anything else? Simultaneity, another idea about time. If one person says 2 things happened at the same time, somebody else might not agree. Okay, well, let's just, those are some of the big ideas of relativity. So first of all, there are 2 theories of relativity. The special one, which is a special case of the general one, and Einstein came up with this special theory of relativity, SR, in 1905. And these are some of the main ideas of it. Yeah, what somebody said, the speed of light is independent of the source and the observer. So I'm just going to kind of lay these things out real fast now and then go into them all in a lot more detail. So, maybe if you've never heard of this stuff at all, it'll sort of start working its way into your brain a little bit. And then by the second time you hear it, maybe it'll make a little bit more sense. Space is 4-dimensional. Now that's a fun thing to say, isn't it? Space-time. Time and space are together in one context. Then some other things that people said, time intervals depend on how fast the observer is moving. Lengths, there's length contraction. Things get shorter when they're moving very fast. C is the ultimate speed limit. It's the law, not just a good idea. Okay? So, and then philosophically, it sort of throws out the whole idea of an absolute state of motion. You cannot say that you are sitting still or moving. I kind of look like I'm standing still here, but the Earth is flying through space at a high rate of speed. Is there anything really different about that? The answer is no. Okay. A kind of unification of electricity and magnetism. And then, nobody said this, but, probably the most famous equation in 20th century physics, E equals mc squared. I should have put it in a bigger font, Anyway, but what's special about the special theory of relativity is that it's restricted to observers that are moving with a constant velocity. Velocity, one of those physics terms, but I think we all know that. Well, the other half of it is the general theory of relativity, and that's the one with black holes, curved space, and all this kind of fun stuff like this. And I tossed an equation up there, but don't worry, you won't be required to solve that until the end of the hour. Right, Jim? Okay. Yeah, and the idea here being, I'm actually going to show, we don't have a pointer in this room, do we? Oh, that would be great, that would be great. Okay. Yeah. What this equation means is that this thing right here is something that tells how space-time is curved. What this thing is something that tells you